Hello friends, today's question. A 20 Henry inductor coil is connected to a 10 ohm resistance in series as shown in figure. The time at which the rate of dissipation of energy, Joule's heat, across resistance is equal to rate at which magnetic energy is stored in the inductor is. So we are given a RL series circuit. Resistance is 10 ohm and inductor is over 20 Henry, and we have to find out the time at which rate of dissipation of energy, rather we can say energy in the resistance, will be equal to the rate at which the magnetic energy is stored in the inductor. So in this case, first of all we are going to find out the dissipation energy, which will be in the form of power, which is our I square R, and then we are going to find out the magnetic energy or rate of energy storage, that is a derivative of, you can say, energy stored in the inductor, and equate them. This will be giving us the time. And for the solution, in this particular case we are given R as 10 ohm. So R is 10 ohm and inductor is given as 20 Henry. So we can find out our time constant, which is our tau, will be equal to L upon R, and this comes upon 2 upon 10, and this is our 2 seconds. And we are going to use the current equation in the RL circuit. You can see the current in the RL circuit, it follows the equation that our IT is equal to our I max, which is also written sometimes as I naught, is equal to 1 minus E minus T upon tau, where I max can be given as V upon R, and which we also call as a steady state current. So let us find out the power dissipation in the resistor. Power dissipated in resistor, we can represent it as P of R, which will be equal to I square R, and we substitute value of I. We are simply going to remove this T function from the I, and we can just write it directly. That will be our I max 1 minus E raised to power minus T upon tau whole square multiplied by R. We simply open the bracket. We can write this as I max square times R 1 minus E minus T upon tau and its whole square. This is our power dissipation in the resistor, and we are going to find out now the rate of change of magnetic energy in the inductor. Rate of change of magnetic energy in the inductor. And the magnetic energy which is stored in the inductor, let us call that UB. Magnetic energy stored in the inductor if represented as UB, which will be equal to half Li square. Rate of storage of energy, we can simply derivate it. Rate of energy storage let us call that PL in the case of inductor, which will be equal to d of dt of UB, and we substitute value of UB, we get d of dt, and this is our half Li square. And we can substitute I as our I max. Let us sort it out here only. This gives us half L 2I di upon dt. 2 and 2 cancels out. This comes as Li di upon dt. And we already know that our I is equal to I max 1 minus E minus T upon tau. If you derivate this equation, we are going to get this as di upon dt will be equal to our I max and e raised to power minus t upon tau, and this divided by tau. So we substitute the values, we get PL will be equal to Li max 1 minus e raised to power minus t upon tau multiplied by I max divided by tau and e raised to power minus t upon tau. We can simplify it a little bit. We can write this as PL will be equal to Li max square divided by tau 1 minus e minus t upon tau and e raised to power minus t upon tau. And in the question it is given that the power dissipation resistance and rate of energy change in the inductor is equal. For that we have to find out the time period t. So using equation 1 and 2, using equation 1 and 2, we have our PR is equal to PL. Under this condition, we have to find out the time t. So let us equate them. We can get this as I square max times R 1 minus E minus t upon tau whole square is equal to L I square max divided by tau 1 minus E minus t upon tau, and this is e raised to power minus t upon tau. We can cancel some common terms. I square max and I square max cancel out, and we can also, I think I missed something here. Yeah, we already know that our tau is our L upon R. We already wrote it here somewhere. Yeah, this is tau over L upon R. So we can say L upon tau is nothing but equal to R. So we can say but L upon tau is equal to R. So we substitute it also. we get this as R1 minus E minus T upon tau whole square is equal to R1 minus E minus T upon tau multiplied by E raised to power minus T upon tau. And R cancels out, and this one of the power of this function also cancels out. So we get this as 1 minus E minus T upon tau is equal to E raised to power minus T upon tau. Now we are almost done with the solution, so we can write this as this will equal to 1 is equal to 2e raised to power minus t upon tau, and this gives us that e raised to power e raised to power t upon tau is equal to 2, or our t upon tau is equal to natural log of 2. And we just calculated our tau. Tau is our 2. We substitute the value. So from here we can say t is equal to tau natural log of 2. Substituting value of tau, we get t is equal to 2 natural log of 2. And if you require, we can further solve it. This will be coming approximately equal to 1.386 seconds. But the answer is only in the natural log form. So option number C is the correct option. So we can say option C is correct. So this completes the question. Thank you.